Good morning to everybody. So, welcome back to this final session of our Atal Computational Science and Biology FDP, jointly conducted by NIT Arunachal Pradesh Basic and Applied Science Department and Atal AICTE. So I welcome our expert, Professor Dr. Parimal Kar sir from IIT Indoor Biotechnology Department to this FDP. So this is going to be his sixth session and final session. I welcome you, sir. And also our session chair, our HOD, Dr. P. Swain sir, welcome. So, yeah, Swain sir, once welcome to you. And I also welcome all the participants to this session. So, this is the last session, okay? So, make most of it. And finally, we have at the end of the session, we'll have some discussions. Hand over the session to our expert. Sir, please.
Good morning, everybody. Let me share my slides. Okay. So I hope all of you can see my slides. Okay. Good morning to everybody, and once again, thanks to Dr. Bhanu for giving me an opportunity to talk to you guys for this entire week. So today we are going to talk about some advanced topics. Okay, and this is called multi-scale modeling of biological macromolecules. Surmounting the challenge of bridging the scales. Basically, I'm going to talk about coarse-scale modeling and multi-scale, how to combine different levels of modeling. Okay, so these are all physics-based model that we have developed for studying the dynamics of biological macromolecules. So I have shown you this figure before also. So the question is, why multi-scale? Okay, so we know that the biochemical processes are inherently multi-scale in nature. They occur on different scales of length and time. So it has varied spatiotemporal scales. And atomistic simulations are several magnitudes away from relevant biological time scale and length scale. That is the main problem. If you want to study a larger biological system, for example, a bigger protein for a 100 of microsecond, then you may not be able to achieve that time scale. Because in the last lecture, I told you that for a molecular dynamics simulation, generally the time step we use 1 femtosecond or 2 femtosecond. So from femtosecond to 100 of microsecond, if you want to come, then you know that how many iterations you have to perform. So that's a huge challenge to us. Not only that, if you represent the entire system at the atomistic level, that is very accurate, okay, but it increases the number of degrees of freedom in your system. And if the number of degrees of freedom increases, then you need to solve the Newton's equation, which is the second order differential equation, coupled differential equation, also 3 times of that. So that also increases. So it means that you need a lot of memory also then, because you need to store the position coordinate. Okay. Not only that, you need a large CPU also. So all these things make actually very challenging these atomistic simulations. Although atomistic simulations are good, but they are not suitable for studying a bigger system for a longer time scales. So they are generally limited to small proteins. So that exactly we have shown here in this right hand panel picture, that quantum mechanics where you resolve basically at the electronic degrees of freedom. Okay, so we say that there is no point charge, rather there is electron cloud. Okay, so that quantum mechanics is the most accurate method, theoretical perspective. Okay, and but if you see that you can use it only for very small number of atoms. That's if you look at the length scale, and the time scale is also very low, very small actually. Sorry, very short time scale. So generally picosecond order that you can study. But you know that the many of the biological phenomena occur at microsecond to millisecond time scales, even second also. So that means it will become almost impossible to use quantum mechanics to study those phenomena. Of course, you can use quantum mechanical method to study some enzymatic reactions, those kind of things, but not large-scale conformation and changes that occur in protein or protein nucleic acid complexes. So for that one, we developed then molecular mechanical method. That is the atomistic method. Okay, so in atomistic method, so again, this is a serial multi-scale model. Why? Because the parameters that you are developing, I mean, you do the calculation at quantum mechanical level of small peptide, and then you derive this k theta, k beta, all those force constant I said, and these bond informations, and then you transfer those values to the molecular mechanics level. So this is called multi-scale. So atomistic simulation, of course, you can use a bigger system compared to quantum mechanical system, okay, for a longer time scale. So generally in quantum mechanics, we use maximum 200 atoms and for a couple of picosecond order. But in atomistic simulation, you can use 100 more than couple of lakhs of atom, and you can run it for microsecond time scale. Okay, but sometimes you know that atomistic simulation may not be enough. You really need to incorporate the quantum mechanical treatment to your system. But at the same time, you know that the entire system does not require this fully quantum mechanical treatment. So then we use a hybrid method. So we just mix quantum mechanics as well as molecular mechanics. We'll talk about it in the after a couple of slides. Okay. So molecular mechanics, then that is the atomistic simulation. So that is, of course, you can use bigger system for a relatively longer time scales, but still that is not enough. For example, if you look at this left-hand panel picture, you can use atomistic simulation for the actin monomer. Okay. But really, can we use it for actin filament? Because actin filament, each filament has 13 such actin monomer. So it's a huge system. And this apactin that you see here, that is the picture that you get from scanning electron microscopy. Okay, so sorry, that's from AFM actually. So now, so it's very difficult if you want to study actin filament using atomistic simulation, because that's a huge system. You can use it, but then you need a huge computational resources, and generally you don't have it. So the idea is that with moderately available computer resources, can we study actin filament for its biological relevant time scale? Okay, so using atomistic, that is quite difficult. So we develop the next hierarchical method. Okay, So this is called coarse grain model. So in coarse grain model, you can see that this third figure actually, which is in coarse grain. So you see that we have drastically reduced the number of particles. So here what we do, we group several atoms into a single bit. Okay, so that is called coarse grain bit. It is a little bit bigger size. So that leads to the reduction in degrees of freedom. So because since you are combining couple of atoms into a single atom, so the overall number of atoms is reduced, and therefore the total number of degrees of freedom reduced. If the total number of degrees of freedom reduced, then the number of differential equations that you need to solve simultaneously will be reduced. So then you require less computational resources. And also coarse grain, since you have less number of atoms, and the force feeder is also not that difficult. So here the energy surface, that the surface I always see, as I showed you yesterday, which looks very rough. There are multiple minimums. So in coarse grain, actually, it becomes relatively smoother. So if it becomes relatively smoother, then it will be easier for you to sample the entire phase space because there is no local minima. I mean, there is local minima, but not many. So it means that the dynamics will also be faster. So now you see that. So the phenomena that you see in atomistic simulation, say in microsecond time scale, maybe depending on the level of coarse graining that you are doing, you can see the same event in couple of 100 nanoseconds. Now you don't need to simulate it for microsecond time scales. Within 400-500, actually, you will get that similar result. So that kind of thing we are talking about. So basically, the idea of doing coarse grain is to accelerate the dynamics and using the less computational resources. Now, if you want to study the cytoskeleton network, can you use coarse grain? No, it is difficult. Actually, why do you need to do it? If you want to study the cytoskeleton network, even if you want to study the networks things, you really don't need to represent everything at the atomistic level or any coarse grain. Because it's a network study, you can use the graph theoretical approaches for that one. So for that one, you can use method we call mesoscale or continuum dynamics. So in continuum, generally in biological systems, the more number of particles, the atoms, come from the water molecules. So the idea is somehow to get rid of the explicit treatment of solvent. It could be water or a membrane, and instead take into their effect implicit way. So that would significantly enhance your simulations. Because, for example, for 20 amino acid polypeptide, you need 2000 water molecules. So 2000 water molecules means 6000 atoms. And 6000 atom means 18,000 degrees of freedom. So if you can get rid of that, then of course your simulation will be much faster. But you should also take into their effect implicit way. Because all the biological macromolecules reside in some kind of solvent environment. You cannot simulate them in gas phase or in vacuum. So for that one, we use this continuum model where we said, now if it is water, then we can say that it is characterized by epsilon is equal to 80. And we say that the effect can also be modeled by this Poisson's-Boltzmann equation. But Poisson's-Boltzmann equation is more accurate, but it's a time-consuming thing. So there is another variant that is called generalized Born model. These are all physics-based models. So that is much faster, but it is less accurate compared to the Poisson's-Boltzmann method. Now the question is, Poisson's-Boltzmann is also an approximation, and GP is also approximation. So you are already losing some error. I mean, you are losing some accuracy by treating the solvent by implicit way. So now, if you make some further approximations, maybe it is good enough. Okay, it may not significantly change the dynamics of your simulation, so you can use it. Now, here, when you treat the solvent at the implicit level and the solute, that is protein or nucleic acid, at the atomistic or coarse-grain level, then you are actually using parallel multiscale model. Why? Because your solute is at the atomistic scale level and the solvent is at the continuum level. You are mixing two different levels together. Okay? You are combining two scales in a single simulation. It's not that easy because you need to optimize your force field such a way that the system remains stable, but that has been achieved. So that is called, as I said, parallel multiscale approach. So there are single multiscale where you derive some parameter at a higher level of method, for example, quantum mechanics, and you can transfer those parameters to the next lower level, that is molecular atomistic. And similarly, you can generate your parameters from molecular mechanics and transfer it to the coarse-grain level. So that is also a serial multiscaling approach. But when you combine this atomistic or coarse-grain representation of the solute and implicit representation of the solvent, then you are performing parallel multiscale simulations. Okay, so that's, you just remember one thing. So now you understand that why do we need different methods to study different biological phenomena. Actin monomer is smaller systems, you can use molecular mechanics. Actin filament is much bigger, you should use coarse-grain model. Now, cytoskeleton network, well, you should use system biology approach. You should use continuum mechanics method to treat it, or you should use mesoscale. Okay, so by mesoscale, what I mean that you can say that one actin monomer is represented by a single bit. Okay, so that kind of thing you can do it. So all these different kinds of methods. So this is how we bridge different scales, both the spatiotemporal scales that's present in biological systems. So we'll not talk about. So today we are gonna first we talk about coarse-grain modeling. Okay. Because atomistic simulation, we talked about it yesterday. So now this coarse-grain modeling. So you know that these computer simulations are indispensable tools in the study of biomolecular systems, including that complements the experiments. So I told you all the time, just keep it, remember that we are performing this all the simulations not to replace experiment. No, our job is to complement experiments. Whatever is not available from experiment, we can get it from computer simulation, and together we can make a complete picture. Okay, so sometimes you see a phenomena in experiment, but you couldn't explain it. For that one, you can perform MD simulations or any kind of theoretical study, okay, to explain it. So the latest generation of atomistic force field combined with powerful computing platforms. Okay, if you have access to Eugene P or Blue Water, so those kind of supercomputing platform, and then if you use some efficient enhanced sampling method, that is replica exchange, So that will increasing the realistic description of biomolecular dynamics. Okay. So generally, this is fine, but however, although such studies are impressive, but atomistic simulations, I said that still there are several magnitudes high from being able to effectively cover both the spatial and the temporal scales of biological system, and that is typically accomplished by coarse gaining. So just remember one thing: this coarse gaining approach. So right now it has mm, attracted a lot of interest. But this method initially was developed by Arya Warsel and Michael Levitt. So they all developed these things in 1976, for which they got Nobel in 2013. But we are not that. He was working on it, but after that, nobody worked on it. Since early 2005-6 onwards, again, people got interested in it, and now it is extensively used these days. So it is, these schemes are not that new. It's just the interest are new, and a lot of people are working on it. So we are developing new methods, actually, new coarse scale models that we are developing. What Professor Arya Warsel did, those are very crude model. Okay, well, I mean, in 1976, but that's the path-breaking work. They show it how to go ahead with it. Okay. Anyway, so many CG models, that is the coarse scale model, okay, of varying complexity have been proposed for proteins since the pioneer work of Levitt and Warsel, I told you, okay. So at the beginning, most of these models were developed with specific applications, such as study of structural features of viral capsid, okay, because viral capsids is really, really big. You cannot use atomistic simulations, at least in those times, okay, where you don't have access to supercomputers. Or the dynamics of protein membrane systems, or protein structure prediction, or scoring, protein decoys, protein-protein docking, and protein folding studies. Okay, so those are developed keeping all those things in mind. And the resolution of CG models may change from one or a few particles per protein to near atomistic resolutions. Okay. So generally, a popular CG representation involves one interaction site per amino acid. So that means one amino acid may have 15 to 20 atoms, and you are grouping all these atoms together and representing a single amino acid by a single super bit. Okay, we will not call it atom, but it's a bit, coarse grain bit. So now if you have a 400 amino acid proteins, then you will have only 400 bits. So you can see that how drastically you are reducing the number of atoms in your system, and thereby the number of degrees of freedom. So it will, of course, greatly enhance the simulations. But the problem is that if you make your model very, very coarse, okay, like 1 bit per amino acids, then you are losing actually too many informations. That may not be good. So those are good. So basically the level of coarse gaining should depend on what you want to study. For certain cases, you may need to have little bit more number of bits, or say if you want to study the cytoskeleton bit, as I said, maybe for that one you can use 10 amino acids represented by a single bit. That is possible. Now, if you want to study the protein folding problem, then that is not a good approach. Then you have to do the resolution at the residue level. Maybe you need to represent each amino acid by 2 to 3 bits. Okay, so this coarse scaling should vary depending on the problem at your hand. Okay, So these are the thing, and also one popular model is the Martini model. Okay, so in Martini coarse grain model, four heavy atoms are represented on average by a single interaction center. Okay, and the ring-like molecules are an exception and mapped at a higher resolution. Up to two atoms are represented by one atom. And in Martini model, I believe they use 4:1 for water molecules. So they represent four water molecules by a single water molecules. Okay. So the model considers four main types of interaction site: the Martini, polar, non-polar, apolar, and charged. And the Martini force field is parameterized based by matching the thermodynamic partitioning free energy of amino acids, side chains between polar and hydrophobic phase. Exactly, they follow the principle of Gromos force field. You just have to remember one thing, that generally we combine all these, the MD, for developing any new methods, you have to compare it with existing model. And that should be at higher level. So for coarse scanning, we set atomistic simulation as our benchmark. Now for Martini, they set the benchmark of Gromos force field. So they have to use the same principle by which this Gromos force field was developed. Okay. Now Martini is most widely used model, and this is generally used to study the protein membrane system. Okay. Now Martini force field has a drawback. What is that drawback? Martini force field, they put a restraint on the secondary structure. So it means that you cannot use Martini coarse grain model to study the protein folding problem. So you just have to remember, that's why I'm saying that all the models are developed keeping in mind what kind of problem you want to tackle. So, and then there is another force field, OPEP. Okay, it stands for Optimized Potential for Efficient Structure Prediction. So that is based on a 6-bit model per amino acid. Okay, so each amino acid is represented by 6 bit, but the backbone is modeled in atomic detail without hydrogens. Okay, while a single centroid bit represents side chains. And then there are other models are also available. That's called prime model, which is by Hall group. Okay, so they use 3 backbone bits, NC alpha C, and 1 minimalist side chain bit C beta. So these are all different kinds of model that there, but every model has some good part and bad part. And they are developed for keeping in mind certain applications. So you cannot just take it and apply for your systems. No, you have to understand the philosophy behind the model. And why did they develop that model? For which applications? You have to know it. So the first model, when this Martini model came, so a lot of people started using it randomly for different systems, and then they published results stating that Martini gives this result. And basically, the developer was really angry because they are reporting a lot of negative result actually. And he didn't develop it for those purposes. Like, for example, if you want to study protein folding problem using Martini, or if you want to study conformational changes using Martini force field. No, that is not possible. Why? Because Martini requires restraint on the secondary structure. If you put a restraint, then how it can undergo changes? It cannot. So then you will say that, okay, there is no conformational changes for this protein, but that may not be the case. Okay, so you have to be very careful in that. So keeping all these things in mind, that drawbacks that is present in the current models, and also one more thing, all the existing current coarse grain models, you cannot reconstruct it back to atomistic model. So we are the first person who developed a coarse grain model, but at the same time, you run MD simulation with coarse grain. But after the simulation, you can convert the entire coarse grain model to the atomistic model. Okay, so that is our strategy. So we developed this model called PRIMO. Okay. So PRIMO stands for Protein Intermediate Model. So this is a transferable coarse-grained model of proteins. Now, why it is transferable and why the other models are not transferable? So by transferable, we mean that just like atomistic force field, the same force field you can use it for any proteins. You don't need to optimize it. You can use it as it is. So it is transferable, it means. On the other hand, many of the coarse-grained models, okay, for example, attract or pace, okay, so those kind of models, you need to optimize it for different proteins. If the protein is changed, you have to again optimize the parameter. So that's why they are not popular. But Martini is not like that. Martini is transferable. You can use it for any proteins. But there is the only problem that you have to put a resistant on the secondary structure, so you cannot use it for conformational changes or protein-protein problem, that kind of thing. Okay. So we wanted to develop a model that can allow us to study the conformational changes of protein. We can study the protein-protein problem also. And at the same time, we want to revert it back to atomistic simulations. So for this one, we have used 3 CG bits, that is coarse-grained bits for the backbone. Okay, so N, C alpha, and combined CO, that is C double band O. So for that one, we use a single bit. Okay, so that means the backbone is represented almost at the atomistic level. And then we use 1 to 5 sites per side chains, and the location and their charges are shown on the right hand panel picture. Okay, so the charges are shown as a color bar, you can see that. So that's how we developed this model. And the best part of our model is that we can reconstruct from coarse grain to we can revert it back. That means we can reconstruct the atomistic simulation. I mean, we can represent, we can get back the atomistic representation from the coarse-grain representation, and the accuracy is 0.1 angstrom. Okay, so before us, nobody did this thing. You are the first who basically did the simulation in coarse-grain and again reverted back to atomistic representation. And in this conversion process, the loss of accuracy is 0.1 angstrom. This one we published in, actually this can also be used as a data reduction technique. So we published this in IEEE transaction also, this technique basically, how to, what is the better way of reducing data, because you need then less storage space. Okay, so you can store it in coarse-grain representation, and whenever you require it, you just convert it back to atomistic. Okay, so that's the thing. So again, I have shown here this ubiquitin in PRIMO representation. Okay, all CG sites are shown as gray, backbone is shown in color, green CA1, blue N1, and red is CO. So, now you see that you need less number of atoms, but I just want to tell you one thing, that in our model, we need more number of CG bit to represent a protein compared to Martini. So continuously, I am telling you that we got the accuracy, better accuracy than Martini, but at the cost of incorporating more number of bits. More number of bits means your simulation will be slower than the Martini. Okay, so there is always this kind of analysis you have to do it. What you want and at the what cost. Okay, so first you need to define the problem. Then only you can go ahead and decide the methods that you want to use or you want to develop. Okay, So now this beam of force field, it has a force field like form that is completely physics based, and it looks like the atomistic force field. And we follow the charm, basically, charm force field that is developed by the Nobel laureate Martin Karplus. So here you see that the first term is the bonded, and that is harmonic potential. However, the second term we added, and that's the spline potential. Why did we add it? We have noticed that generally this spline potentials are required because this complete harmonic potential may not be able to capture the anharmonicity present in your system. So to capture non-harmonic potential shapes and the presence of multiple minima, we use this kind of spline potential. Okay, the same thing, and then also we have constructed the third term. You just look at it, Ki virtual bond. So we have constructed some virtual atoms actually. So for some side chains, we just noticed that the regular bonded term and the spline potentials are not sufficient to maintain stereochemically correct geometries. So in those cases, the primary primo interaction sites are augmented by virtual atomic sites. So that is the third term that we have added. Okay, that are reconstructed on the fly from the primo side. So thereby, since you are constructing on the fly, so that means you are avoiding additional degrees of freedom. So you are, and remember one thing, they are not taking part any non-bonded interactions. I repeatedly told yesterday that the molecular dynamic simulation is slowed down because of the electrostatic and van der Waals interactions, because those two interactions are pairwise interactions. Those are non-covalent interactions. So if you make sure that these virtual bonds, the virtual atoms that you are creating on the fly, and they are not taking part in non-bonded interactions, then you don't need to worry, because that will not add any extra cost to your simulation. So they take part only in the bonded thing. Okay. So we added this spline potential for bond, angle, and torsion. For all these three bonded terms, we constructed these things. Okay, and then as usual, we have this van der Waals and the electrostatic potential energy, and finally we use this the fourth one, which is colored by this red box. So that corresponds to the hydrogen bond interactions actually. Okay. So how would you take into those hydrogen bond interactions? So that, and this is, we have used explicit angle and distance dependent hydrogen bonding potential. Okay. Cos alpha and H, so those are angle and distance dependent. Okay. And this is a knowledge based potential in this entire force field. Okay. And the next term is the solvation term, and the last one is the for the non-polar interactions. Okay, so for this force field, all the terms, those are all physics based. Only this for the hydrogen bond interactions, we have used knowledge based term. Otherwise, all are physics based term. So even the solvation model that we use, we have combined generalized bond, molecular volume approach, and atomic solvation parameters. Okay, so everything is based on physics, and we optimize. Now, once you have a force field, you have to optimize it. And I said that atomistic models are developed, optimized with respect to quantum mechanics. Okay, now Coarse-grained models are lower resolution than uh, atomistic model. So for optimization of coarse-grained models, we have to set atomistic simulation as our target. So here we take charm as our benchmark. We want to optimize our force field and try to match with charm atomistic force field. Martini was developed by matching with the Bromos atomistic force field, and our Primo is based on charm force field. Okay, this is mainly because it depends on from which group you are. So since we belongs to the charm group, okay, developing group, so we use charm as a modeling as a standard benchmark. Okay, so now these virtual atoms, we need to, I said that we constructed these virtual atoms on the fly because that enables better bonding geometry, okay? And the main thing is that these virtual atoms do not participate in non-bonded interactions. Now here I have shown you for this particular cases, phenyl aniline, okay? So this shows the treatment of phenyl aniline as an example. For this residue, the primary CG sites are located at SC2 and SC3 and SC1, okay? And the midpoint between C beta and C gamma, that is SC1. Now, on the basis of stereochemistry, the sampling of the SC1 particle, okay? SC1 particle should be restricted to a circle around the C alpha C beta bond because of sp3 hybridization of bonds to C beta. However, the angle terms such as N1, C1, SC1, okay, that I have shown on the right hand panel, that figure, okay, and other bonded terms are insufficient to maintain the SC1 particle on such a circle. So as a result, the Primo model will result in non-chemical structures when reconstructed to all atoms. Now, you can ask, then why didn't the other model use it? Other models, they didn't use virtual atoms because they are not interested to take it back into, reconstruct it back to atomistic model. The problem you occur only when you reconstruct it back to atomistic model. And that's what you want to do. That is our USP. Okay? So, an additional issue with phenylalanine is the planarity of the aromatic ring. That is not maintained with just the 3 primary Primo sites. So to alleviate this issue, 2 virtual atoms, C beta star and C gamma star, are introduced that are reconstructed on the fly. So now you see this right hand panel picture. Without virtual atoms, you have the blue color. It is so white. Okay? And the all atom is the red one. It is so narrow, you can see it. Now, if you add the virtual atoms, then you look at the sampling. So that corresponds to the green one. It is more like the atomistic. Okay? So that is the utility of constructing virtual atoms on the fly, which enables us to maintain a better geometry without costing additional simulation time. Okay? So now this is the force field optimization strategy that we have used. I don't want to talk much about it. Okay, this is 2 technical things. So these are basically, we try to match with the solid car, that is black curves is the atomistic, and the red one that we get from our simulation. So you see that how did we match? So the matching is so exact. You can see that we fitted it really nice with the atomistic model, this coarse-grained. Now for the below 2 figures, okay, you see that you have more than 1 minima. You have multiple minima. So for that kind of modeling, we have used spline potential. In addition to simple harmonic potential, we have added the harmonic potential just to, the spline potential to model this higher order minima. Okay. But in no other coarse-grained model they use the spline potential. Let me tell you that. Now see the energetic matching between the atomistic and the Coarse-grained model that we have developed. So this figure actually shows that thing, and the correlation you see is 0.9. It's basically strongly correlated with the atomistic energy. So this ensures that the model or the that we have developed is very good, and the way we have optimized all the parameters is accurate enough to reproduce atomistic result. Okay, and then another thing is the Ramachandran plot, that is the phi psi angle. Okay, so this tells you what are the allowed and disallowed regions a protein can have. Basically, all these amino acids can convert, because all these alpha helix, beta sheet, coil, all these different structural characterization of proteins that we do actually, that is characterized by this phi psi angle. So the left hand panel that corresponds to the coarse-grained, and the right hand panel corresponds to atomistic simulations. And you see that we have been able to capture the minimum in our simulations. It should not exactly match, but overall we have captured the main minima present in the atomistic simulations. So this also ensures the quality of the model that we have developed. So once we do the quality checking and everything, then we apply it. We want to study the dynamics of protein. So we perform molecular dynamics simulations. Now you see one thing here. For atomistic simulation, I say we use a time step of 1 to 2 femtosecond. But here I have used a time step of 4 femtosecond. Okay. So now we have this 11 proteins. We have done the simulations, and you can see that for all cases it is stable simulations. And the average deviation that you find that ranges between 1.8 to 4 angstrom. On the other hand, the same protein deviates from 0.8 to 2.8 angstrom in atomistic simulations. So overall, we maintain the geometry of the structure. Now you see that I have reconstructed back the coarse-grained model to atomistic model and superimposed on the experimental structure. That you can see the green one corresponds to the simulation, and the red one corresponds to the experimental structures. Okay, so that is the thing. We completely reconstructed back to atomistic, and the error in this reconstruction process only 0.1 angstrom. The method that we developed, when we compare it with the atomistic simulation, we found that our method is 25 to 30 times faster than atomistic simulations. So it means that the same protein that you can run for 100 nanoseconds, using our method, you can run it for 100 into 30. You can run it for 3 microsecond time scale. Okay, so now you see that why do we need to develop these kind of models? Now I want to talk another technique. Okay, so yesterday I promised that often we not only use MD simulation or Monte Carlo simulations, we use a hybrid method. We combine both MD and Monte Carlo together in single simulations. So that method is called the parallel tempering or replica exchange methodology. Okay, this is just to overcome this energetic barrier that is present in the protein or biological macromolecules. Okay, so the REM or replica exchange or PTU or the parallel tempering, okay, that consists of M non-interacting copies or replicas of the original system in canonical ensemble. Canonical ensemble means NVT. That is, the number of particles is fixed, volume of the system is fixed, and the temperature is fixed. Okay, at M different temperature. So each copy is, or each replica corresponds to a different temperature. You have M number of temperature and you have M number of copies, and each copy is assigned a different temperature. Okay. Now, each replica in canonical ensemble of the fixed temperature is simulated simultaneously and independently for a certain Monte Carlo or MD step. Okay, so suppose you run for 5 picosecond of MD simulation. You have to run all the replicas simultaneously. So if you have 200 replicas, then you have to run these 200 replicas simultaneously. So at least you need 200 processors. If you have 64 replicas, then you need 64 processors because all things should run together simultaneously. Now you have to take a pair of replicas. Those are from the neighboring temperature and try to exchange them. By exchange, I means copy the configuration of higher temperature to lower temperature and the lower temperature to higher temperature. That is shown in this figure here. Okay, the replication scheme that I have shown. Now, whether you will accept it or reject this move, that is determined by the Monte Carlo metropolis criteria. So you are introducing Monte Carlo concept here. So you are running each replica for a certain stage of MD simulation. Then you employ the Monte Carlo criterion, try to exchange it. If it is accepted, copy the moves, copy the configurations. If it does not, then let it be there and run again 5 picosecond of MD simulations. Then again try to exchange the confirmations using the metropolis criterion. And you have to make sure that you have to choose this temperature such a way that their potential energy overlap with each other, but they should not completely overlap. There should be 30 to 40% of overlap. Okay, you have to make sure that the exchange probability should vary between 20 to 40%. If you say that, okay, I will develop a method that will have 100% exchange, then you won't have a better sampling because then there is no randomness. It's a certain thing that all the moves are accepted. That you don't want. You want to introduce probability into it. Okay? You want to introduce randomness so that there is no bias. So that's why you have to make sure that there is this exchange frequency. This exchange probability does not go beyond 40% actually. Okay, so what you are doing actually, in principle, you are performing a random walk. You are performing a random walk in the temperature space, and temperature corresponds to energy. So basically, in principle, you are performing a random walk in the energy surface. So now you can see that here we have run, basically this is schematic representation, 4 temperatures I have shown. So you see that the 300 Kelvin within 3 steps we have reached from 300 to, the confirmation has reached from here to 375 Kelvin. The 375 Kelvin confirmation has also reached to 325 Kelvin. So that way you are overcoming the energetic barrier. When you are copying the confirmation from higher temperature, so it has a higher energy to a lower. So that means you are copying like this. This jump is there, and the lower to higher. So this also jumping this energy barrier. Okay, so that way you are overcoming the multiple minima problem. Okay, so this is also basically optimization techniques. This is a statistical mechanical approach, and this is widely used. Only problem is that you need a very large computational power because the number of replicas depend on square root of number of atoms. Now, if you have more number of atoms, so then you know that how many, it will drastically increase. Okay. So now, if you represent your system at the atomic core scale level, so the number of atoms reduces. So you need less number of replicas. So then you can run it in a moderate size HPC cluster. Okay, so that's exactly what we did here. So these are the 4 different polypeptides we simulated. Okay, some are alpha helix, some are beta sheet, and we use this replica exchange technique. And you see that, and we started from the complete linear chain. We started from the sequence. We fold it to the experimental structure. The PDB, whatever it is written, that is the experimental structure, and rest are just whatever we get from our simulations. Okay, so now you can see that we have been able to fold from the sequence to three-dimensional structure, and the deviation that we get within 2 angstrom from the experimental structure. That's a great achievement, and it is much, much faster. And let me tell you, the charm force field cannot hold GB1 to beta sheet. Even the amber force field also, they make it actually GB1, this peptide, the second one, in amber, they make it helix. But the experimentally determined structure is beta sheet, beta hairpin. But using Primo, we have been able to hold it into beta sheet, which is otherwise not possible even in charm atomistic force field also. Okay, so these are the different things, and all this percentage that we get, that we got from the K-means clustering. That's the machine learning approaches that we have used to get all those things. That's one thing, and then the final thing I want to talk about is so that is for soluble protein. The same thing we can model it for the membrane protein also. So the membrane is generally bigger thing, okay, if you represent it to atomistic level. So I said that for water is characterized by a dielectric constant of 80. So that's why we use, we characterize the solvent environment by dielectric medium. The same thing can be done for membrane also. Okay, so membrane can be represented, instead of using a single dielectric constant, we can use multiple dielectric constant. Okay, so that exactly we can do it, because this is how I show it. Okay, the first figure actually the dielectric constant, how it varies. So the center of the membrane is very hydrophobic. So that thing you can model it using solvent cyclohexane. Cyclohexane has a dielectric constant of 2 to 4, and exactly that represents the membrane core. And then the interface between the membrane and water, that can be modeled by octanol. That solvent, that has a dielectric constant of around 40. Okay, so that exactly we did. So this is how we are modeling it. Okay, and these are the different equations that we use. We do not talk about it. Okay, how we basically that's how we use it to model. And then we, as I said, first we need to match with the atomistic simulation. So first we study the insertion energy. So you have amino acids at the center of the membrane, and you are pulling it. You are pulling from the center of the membrane to the water environment. So how the energy changes? That is how it is changing. And you see that the orange color corresponds to the Corscan model, and the green corresponds to the atomistic simulation. And it exactly matches with the atomistic model. But the problem is for the charged amino acid. Why? The center of the membrane is hydrophobic. Now, if you put a charged amino acid in the membrane, how can it remain there? It's a charge. It wants to interact with water. So what would happen to the membrane? So the membrane will bend. Membrane will bend, and there will be a narrow water channel. Okay, there will be a water pore, so that the amino acid at the center of the membrane sees the water and interacts with it. Then only it can remain stable. Otherwise, it will never ever stay there. It will just come out. So for that one, we use a different kind of membrane model. Again, that is also implicit model. Okay, dynamic DHDGP. Okay, dynamic. We take into account that. We use again a different kind of elastic model. Okay, for that one. And now this is the insertion energy that we get, and it exactly matches with the the atomistic simulations. And then we matches with the experimental result also, and you see that our result degrees. I mean, the correlation is 0.9, near perfect correlation. We got it with the experimental result. Okay, although it's a Corscan model, Even the membrane also, we represent it at the continuum level. Okay, the solute at the core scan level, and it's a multi-scale approach, and the membrane at the continuum level. Still, when we combine these two approaches, we are getting very good matching with the experimental result. This is because our our optimization strategy is very, very good. It's robust. Okay, and then you also study the dynamics of different membrane proteins. As you can see, they are very stable. And again, this is 35 to 40 times faster than the regular atomistic simulation of membrane protein. So you can imagine now how bigger systems you can study for a longer time scale using this core scale model. Then another problem is how to, so generally the membrane proteins, they tilt in the membrane, okay, because that determines their function. We can also determine their tilting angle. This is, and it agrees with the experimental study. You can see that Primo we got 9.1 and experimental is 11. Okay, so basically it agrees very well with the experimental study also. And then you also confirmation the study. I don't want to talk about this because time is running fast. I just want to go to another, which is the latest model, that is hybrid model. Okay, how to combine atomistic and core scan. I said that many of the cases you may need to represent, you need to have quantum mechanical method, or you may need to have atomistic model present. But in those cases, you don't need to represent the entire system in atomistic level. Maybe you are interested only to study the protein-drug interactions. So that means you need to represent only the binding site at the atomistic level, and the rest of the part you can keep it as core scan level. So that will also enable you to run the simulation for a longer time scale. Okay. And also it is not needed because you just want to interest in only the protein-drug interactions. The drug does not interact with the entire protein, only a couple of residue in the binding site. So we should develop a model by assigning atomistic representation of those small subset of residue, and the rest of the amino acids should be represented at the core scan level. Now here, we develop this model, we have three different levels are present. The protein is represented at the atomistic as well as core scan level, and the solvent is represented at the continuum level. So we are combining all these three different scales together, and we hope that it will work. So we achieve it by so the right part is the atomistic, and the left part is the atomistic, and the right part is core scan representation, our model. So the main thing is how would you connect? How would you make the bond between the atomistic and core scan? Because core scan are really not the atoms, because they are basically representing a bunch of atoms. So how do you make them the connections? How the bond is formed between them? With Primo, we can do it. This is how we do it. Okay, the atomistic, this carbonyl carbon and the nitrogen from the Primo, they form a direct bond, and then there is this 3 makes angle parameters here. Okay, now here you see that the N from the right hand side, Primo, that is, although we are calling it CG side, but you know that this is the backbone and we have not disturbed the backbone. So it is possible to connect with that, okay? Because both are, from both sides, these are atomistic representation. And this angle also CA, C and N, that is also atomistic nature. And C, N, C alpha is also atomistic. Only thing is this dihedral angle, okay? C, N, C, A, and that C, this is actually, we take it from Primo. This dihedral angle, and similarly this dihedral angle also we take it from the Primo. Okay, but that diangle that I showed, that I take from atomistic. So this is how we did all the parameters. We didn't optimize anything. We are taking either from the atomistic or taking from our core scan, and that's why we are saying that our model is fully transferable. We don't need to make any changes. Take any protein and you can just do the simulations as like you do it with the regular conventional atomistic NT simulations. Okay. And here, finally, the Hamiltonian of this mixed system would be represented by the Hamiltonian, that is the force field of AA, that is all atom, plus UCG, that is of course gain, then plus UAACG, that is the for the mixed cases. Okay, so that's exactly we did it, and then we run simulation for 3 different proteins, and we use AACG. That is the first one is the model that we developed. Then the third one is the atomistic simulations. Okay. Second and third are the atomistic simulation, and the fourth one is the only coarse grain simulations. So now you can see that by introducing AACG, you are in. If you compare with only, that is the last row with the first row, okay, because last row is pure coarse graining, and the first row is the multi-scale approach. So now you can see that by introducing this multi-scale approach, you are providing more stability. The simulation is much better than only primo simulations, the only coarse grain simulations. It is much more mimicking the result from atomistic simulations. Okay, so that is the utility. This is the same thing, and then we also study basically this kinase conformation and transition using this method. Okay, so the core region that is shown in pink color here, and the AMP binding domains are also shown. Okay, so here the lead and AMP binding domains undergo large conformation and change from open to close in presence of magnesium, ATP, and AMP. So that we want to study without those ligands what is the preferred conformations, and we found that. So we perform again a different kind of simulations here. I have not told you this method. This is very advanced method. This is called umbrella sampling method. Okay, so using this AACG method, we found that this AACG method, okay, this blue line exactly matches with the A, that is the all atom result that you can see. Both cases the minima are located at the same position. So our simulation matches with the all atom simulation, and it states that the open like conformations are energetically more favorable than closed conformation for this adenylate kinase when the ATP is not bound to it. So you can study all these different things using AACG or the coarse grain models. Of course, when you use AACG, then you are introducing better accuracy. But again, the speed up will be less compared to pure coarse grain, but speed up will be much higher compared to the pure all atom simulations. Okay, so you need to use all these different kind of methods or models based on the questions that you want to answer. Okay, that is the main thing. So I'll stop here. Thank you all. Okay, and if you have any questions, you can ask me. I don't want to go much deeper.
Sir, yeah, sir. Thank you for this session. Am I audible? Hello?
I can hear you.
Yeah, sir. Thank you for this session. Yeah, this floor is open to
yes, sir, you are audible.
Participants. Kindly, if you have any questions, you can have a discussion.
Okay. Yeah. Well, I mean, Hamiltonian is the force field. I told yesterday that chemists say force field and physicists say Hamiltonian. Hamiltonian is nothing but the potential energy functions. Okay, so here basically in primo in coarse grain model, I told you that the regular force field, okay, that I talked about yesterday. So it has only 5 different terms. Okay, the bonded terms, okay, that is these three different bonded terms, which are represented by harmonic potential, and then two non-polar, non-covalent terms. Okay, those are atomistic, this electrostatic interactions and the van der Waals interactions. Okay, the van der Waals interaction is represented by Lennard's potential, and the electrostatic interaction is represented by Coulombic interactions. Okay, so what I'm saying that since core scanning we are reducing the number of atoms drastically, it is often very difficult to keep the geometry of the stereochemical geometry actually intact. So that's why you need to add something more. Okay, so we are adding splitting potential, because I told you that if you see this figure, it is easier to model this, from atomistic, when you have a single minima. Of course, you can use simple harmonic potential for that. That we are doing. Now, why do we need additional spin potential? That is required when you have, just look at it, when you have multiple minima. How do you model that using a simple harmonic potential? Okay, for that one, we are using spin potential to do that thing. That is the difference only. Okay, and now hydrogen bond also, it is very important that can keep the proteins intact. So now, since you are drastically reducing the number of atoms, so basically it's very hard to then tell which atom will form hydrogen bond with others. So that's why we are using this knowledge-based potential that is generated from scanning experimental structure. So we have just scanned 1 lakh of experimental structure and then make this thing. Okay, so this is pure knowledge-based potential. And the other terms are solvation terms. So I told yesterday that solvation can be represented by Poisson-Boltzmann, or you can use generalized bond model. Poisson-Boltzmann is more accurate, but it's very time consuming, so we use generalized bond models for this one. So that's all actually. So that is the Hamiltonian. The Hamiltonian is basically the sum of kinetic energy and potential energy. So you can write this Newton's law, okay? You can convert it to the momentum space also, no? So kinetic energy Ke is equal to half mv square. So P, that is momentum, is equal to mv. So kinetic energy, you can write it P square by 2m. So you can convert it into momentum space, so that will be your Hamiltonian. Okay.
Yeah, participants, any other questions? If you don't have any questions, then I just would like to thank our expert, Professor Dr. Parimal Kar sir. He has been wonderful with us for the past 1 week. So on behalf of again our director, Professor Dr. Pinkeshwar Mahanta sir, our HOD, Dr. P.K. Swain, our institute, NIT Arunachal Pradesh, and as a coordinator, and our sponsors, AICTE, Atal. So I thank our expert for this wonderful 6 hours of sessions. So a lot of efforts, a lot of time, a lot of energy might have gone into this for him and his team, of course. So we thank you, sir, and we would personally, as well as on behalf of our institute and the department, we would like you to visit NIT Arunachal Pradesh sometime in the near future, once this COVID situation comes down. So we would just love to invite you for that. This may be a personal invitation. Sooner we will get a chance, I believe, because naturally people would like to visit the places during this workshop. Human to human contact must be there. And of course, this online will also
I agree.
go on. So yes, sir, yes, sir. Yes, would you like to say something, sir? Yeah, sir. Please. Okay. It actually started at during the month of May. Actually, we visited IIT Indore. So there I saw sir, and he was the coordinator of data science and analytic
Data science.
programs. So he readily consented. Yeah, readily consented to come to NIT Arunachal. But fortunately or unfortunately, this COVID situation came, and we were restricted to online meetings. So once again, I invite you, sir, to NIT Arunachal Pradesh, and from my bottom of the heart, I would like to thank you. We know what is the effort administrative teaching and research schedules. So you have taken out this time. Really thank you for giving us an opportunity and sharing your expertise with us and our participants. So I thank you very much, sir, on behalf of all of, especially the Atal and NIT Arunachal Pradesh. Thank you, sir. Sir, participants and sir, please don't go away. I will stop this recording here, and you can have some informal discussions with the sir, because sir also required some feedback, sir. He required feedback, no?
Yeah.
Yeah, so I will just stop recording. Then to sir, if he will spend some time